Now we've formulated the RSA theorem, it's relatively straightforward to prove it. So just again, here is the statement of the theorem. You have two primes, p and q, which are distinct. N is their product. M is the product of p minus 1 and q minus 1. E and D are numbers bigger than or equal to 1, less than m, where the greatest common divisor of E and M is 1, and DE is equal to 1 modulo m. We also assume that W is bigger than or equal to 0 and less than n. C, which is the encrypted number, is W to the E modulo n. And then D, which is the decrypted number, is C to the D modulo n. The claim of the theorem is that D is equal to W. And as we saw before, this is the same as saying that W to the E, all raised to the power D, is equal to W modulo n. So now for the proof. So we want to show that, in fact, W to the power ED is equal to W modulo n. We've used nothing more or less than the following, that with ordinary integers A, B and C, that A to the power B all raised to the power C is just equal to A to the power BC. So that gives us that this is actually equal to that, just as ordinary integers, just in the sense of ordinary integers. So we want to show that n divides the difference of this and this. Because n is the product of the two primes p and q, that means that p must divide the difference and q must divide the difference. And equivalently, if they both p and q divide the difference, then so does n. We use the fact there that p and q are distinct. So we want to show that. Now, we may as well just do the p case. It's going to be exactly the same in the q case. So first of all, a very simple case to get out of the way is suppose that p divides w. That means that w is equal to 0 modulo p, so w to any higher power will also be 0 modulo p. So both sides are equal to 0, and the result's immediate. If p does not divide w, then w to the ed, which is what we're interested in, is equal to w to the km plus 1 for some k, because ed, remember, or de, is equal to 1 modulo m. So that means that ed minus 1 is a multiple of m. In other words, ed is equal to km plus 1 for some k. So now we can pull the factor, we're just working with ordinary integers here, we can pull the factor w out the front and we have times w to the km. M, on the other hand, is p minus 1 times q minus 1. So we can write this now, w to the k times p minus 1 times q minus 1, we can write that as w to the p minus 1, all to the power k times q minus 1. It's just another example of what we had before, that a to the b to the c is equal to a to the bc for ordinary integers. Now what we use is that we're going to work modulo p. So far, everything down to here has been true for ordinary integers. Now working modulo p, we're going to use Fermat's little theorem, and because p does not divide w, that means that w to the p minus 1 modulo p will equal 1. So I can replace this by 1, keeping the power k times q minus 1. So we now have that w to the ed is equal modulo p to w times 1 to some power. But of course, 1 to some power is just 1. So therefore, w to the ed is equal to w modulo p. So we've used Fermat's little theorem. The q case is exactly the same. So that's the proof of the theorem. Someone might say the proof of the theorem should be even simpler, because if de is equal to 1 modulo m, then we just replace de by 1 here. Now that's wrong for a number of reasons. First of all, de is equal to 1 modulo m, not modulo n. And secondly, even if it were the case that de were equal to 1 modulo n, Still, that would not help. We saw before when we discussed exponentiation that it's not the case that if two powers are equal to one another modulo n, then a to the first power and a to the second power should equal one another modulo n. The only result like that is Fermat's little theorem, which says that a to the p minus 1 is equal to 1, which is a to the 0, modulo p. So p has to be prime, and p minus 1 in any case is not equal to 0 modulo p. So that idea that ED is equal to 1 modulo m could be useful. It doesn't help.